Hello, welcome to this 12-minute supplement on Hawking radiation for the Gravitation and Black Holes course. The lecture script for all the supplemental videos is available at a link given in the description of this video. Hawking radiation is thermal radiation that is theorized to be released just outside a black hole's event horizon because of relativistic quantum mechanical effects. It is named after the physicist Stephen Hawking, who developed a theoretical argument for its existence in 1974. In classical mechanics, total energy is always conserved at all times. In quantum field theories, energy fluctuates over short times, but is conserved over longer times. In this diagram, space is horizontal and time is vertical. The interaction can borrow energy from the vacuum and then shortly return it within limits. Particle-antiparticle pairs can be created from the borrowed energy. They are virtual particles with the same mass energy as one another and the same properties mostly as real particles, except that the particle's existence is very short-lived. The particle and antiparticle soon annihilate one another and return the borrowed energy to the vacuum. It's similar to balancing the books in an accounting sense or borrowing from petty cash and quickly returning the money. There is a borrowing time that depends on the amount of borrowed energy. This interaction can borrow 1 million electron volts of energy from the vacuum to create a virtual electron and positron pair, but that pair must annihilate and vanish and return the borrowed energy within 3.2 times 10 to the minus 22 seconds. In that interval, the virtual particles can move no more than 10 to the minus 13 meters from one another, or 100 times the radius of a proton. After this fleeting time and distance, the virtual particle pair vanishes and energy is again completely conserved. Because of this, the vacuum is not nothing. The vacuum is a sea of virtual particle-antiparticle pairs, continually created from the vacuum and returning to the vacuum. This vacuum virtual particle pair creation and annihilation occurs everywhere in the universe. It occurs in the vacuum of space, but it also occurs inside atoms, inside our body. It occurs very near the electron, every electron, and very near every proton, even inside every proton. This vacuum virtual particle pair creation and annihilation also occurs just outside the event horizons of black holes. What happens if one of the virtual particles crosses the black hole event horizon and the other does not? When one virtual particle crosses the black hole event horizon, it can never return to the outside universe. The virtual particle that did not cross the black hole event horizon changes from a virtual particle to a real particle, and it has real positive mass energy. this particle could potentially escape from the black hole, and this is called Hawking radiation. The energy borrowed from the vacuum upon the creation of the particle pair must be returned promptly to the vacuum, and this occurs by the mass of the black hole decreasing by the mass energy of the particle. By this Hawking mechanism, black holes can lose mass, even though no particle crossing the event horizon of the non-rotating Schwarzschild black hole ever escapes. Physicists believe that Hawking radiation probably exists, though it has not been observed or confirmed. The only other theoretical mechanism for a black hole to lose mass is for some mass inside a rotating black hole to escape to another universe. But that is not Hawking radiation. If the particle crossing the event horizon had electrical charge, the black hole acquires that charge. But other elementary particle properties such as baryon number and lepton number do not affect the black hole's properties on our side of the event horizon. Virtual particle pairs can include photons, electrons and positrons, neutrinos and antineutrinos, quarks and antiquarks, protons and antiprotons, etc. Hawking's theory says that Hawking radiation is thermal, blackbody radiation emitted just outside the event horizon, with a temperature measured by a faraway observer of this expression. The temperature is inversely proportional to the black hole's mass. This is a small number, a small temperature. The Hawking temperature is extremely low for stellar mass and supermassive black holes, where the denominator is going to be larger than the numerator, much lower than the cosmic microwave background temperature. So those black holes are absorbing more energy from the cosmic microwave background than their Hawking radiation is emitting, and their mass is increasing. The Hawking radiated power, or luminosity, of the black hole is this expression. This power is extremely low for stellar mass and supermassive black holes. If the black hole is not absorbing any mass energy, such as from an accretion disk, and its temperature has been much higher than the cosmic microwave background temperature, then the time that the black hole takes to evaporate completely and no longer exist is this expression. For stellar mass and supermassive black holes, this expression is going to be greater than 1, and the evaporation time is many orders of magnitude longer than the age of the universe. And also, their temperatures are much lower than the cosmic microwave background temperature, so they're absorbing more energy from the background than their Hawking radiation is emitting, So their mass is increasing, and this formula is not even valid for stellar mass and supermassive black holes. However, this formula is valid for very small masses, much less than the mass of the Sun. If the mass of a primordial black hole is much less than the Sun, its temperature will be higher and could be higher than the cosmic microwave background. In that case, the numerator here will be smaller than the denominator, and the evaporation time will be lower than this number, and it could be quite low. A primordial black hole with the mass of the Great Pyramid of Giza, which is 6 billion kilograms, would evaporate in less than 1,000,000 years. So lower mass primordial black holes that might have been created in the Big Bang might have evaporated by now. But masses over 200 billion kilograms could still exist. Scientists have not yet detected evidence of primordial black hole evaporation. Physicists do not have a verified theory of quantum gravity which could change Hawking radiation.